Hello and welcome to the Screencast introducing key features of rational functions. In calculus, one of the most important ideas is the instantaneous rate of change, and the instantaneous rate of change of a function arises naturally from the average rate of change. For example, we'll say that the instantaneous rate of change of the function s of t at t equals 2 is the limit of the average rate of change, where the average rate of change from 2 to 2 plus h equals negative 16h plus 16h squared divided by h as h approaches 0. In other words, for the rational function that defines the average rate of change from 2 to 2 plus h, we are interested in the function's behavior precisely where the function is undefined. And this leads us to think about that behavior at a collection of very small values of h. For any rational function, we can ask and explore similar questions. For example, if r of x equals the quantity x squared minus 1 divided by the quantity x squared minus 3x minus 4, we can study the behavior of the function near several interesting points, including x equals 1, x equals negative 1, and x equals 4, which are all of the locations where either the numerator or the denominator is 0. And we will see that sometimes these values of x for a rational function lead to either points where the function crosses the x-axis, sometimes to vertical asymptotes, and sometimes to unusual behavior that a computer graphing program fails to detect. In addition to considering the behavior of rational functions up close at important x values, we can also study their long-range behavior to see if they demonstrate asymptotic behavior. Here, like with polynomial functions, we use the language and notation of limits and consider expressions such as the limit of the polynomial x squared minus 1 divided by the polynomial x squared minus 3x minus 4 as x increases without bound. The long-term behavior of polynomial functions helps us to understand the long-term behavior of rational functions. Indeed, the degree of both the numerator and the denominator will end up playing a key role. As with all of our work with functions, it's important to think about patterns and trends and the types of behaviors we expect to see within families of functions that have similar algebraic structure.